Hi there, welcome to this Alchemist chemistry video looking at the rate equation. So, the rate equation provides quantitative information about how the concentration of reactants influences the rate of reaction. What we're going to do now is going to break down the key components of this example rate equation to explain what each of the symbols means. First, we'll start with the rate constant given the symbol K. This is a proportionality constant which relates the concentration of reactants to the reaction rate itself. Whilst we say that K is a constant, it will vary with different temperatures. The higher the value of K, the faster the reaction. The lower the value of K, the slower the reaction. Next, I'd like to deal with orders of reaction. These are the powers to which the concentrations of reactants are being raised in the previous rate equation. Orders of reaction tell us the extent to which the reaction rate is affected by the change in concentration of a particular reactant. For example, if through experimentation we found that the rate of reaction was unaffected by the change in concentration of a particular reactant, we conclude that this was zero order with respect to that reactant. In other words, change in the concentration of the reactant had no effect on the rate of reaction. Therefore, this reactant would not appear in the rate equation itself. So let's look at reactant A, for example. If we found for experimentation that doubling the concentration of A also caused the rate of reaction to double as well, this would mean this is first order with respect to reactant A. In other words, there's a directly proportional relationship between changing the concentration of reactant and its effect on rate of reaction. When A doubles, the rate doubles. Hence it appears in the rate equation. Let's now turn our attention to reactant B. If, for experimentation, we find that doubling the concentration of B causes the rate of reaction to quadruple, this would mean it's second order with respect to reactant B. In other words, there's a squared relationship between the change in concentration of the reactant and its influence on the rate of reaction. Hence, B appears in the rate equation and has a squared power, or a power of 2, to the right-hand side of the concentration to show that it is second order. Now we're going to learn how to rearrange the rate equation. For example, what if we wanted to make K, the rate constant, the subject of this particular equation? Well, if we divide both sides by A times B squared, this would cancel out the A times B squared from the right-hand side and divide rate by A times B squared on the left-hand side, therefore isolating the value K, or the rate constant. So doing this would rearrange the expression into this form, making K the subject and allowing us to calculate a value for the rate constant K, which is often the objective of the question we're being asked in A-level questions. Just want to quickly segue into how to calculate overall orders for expressions. For example, for this particular rate equation, if we were asked to calculate its overall order, we multiply A to the power of 1 times B to the power of 2. When you multiply indices or powers, the indices rule that applies here results in us having to add those powers together to find out the overall total. So we take 1 plus 2 for the two powers, giving us an overall order of 3. So the final thing I want to cover at this point in the video is how to calculate units for the value K, the rate constant. So we've got our expression rate divided by AB squared. Firstly, we want to replace those symbols with the units for those particular values. So rate is measured in moles per litre per second, and concentrations are measured in moles per litre. You will notice we have the same unit above and below the division line in the numerator and denominator positions, the mole per litre, which will therefore cancel each other out, leaving us with a simplified version of S to the minus 1 divided by moles per litre squared. So what we have there is mole to the 1 dm minus 3 multiplied by mole to the 1 dm minus 3. So we add the indices together, 1 plus 1 and the minus 3 plus the minus 3, giving us S to the minus 1 over mole 2 dm minus 6. Now we're not allowed to leave it in this fractional form, but fortunately another indices rule comes into play here, because it turns out that 1 over x to the power of n, for example, is equivalent to x to the power of minus n. So in the same way we can apply this exact rule to our unit shown. So effectively we're going to flip our mole 2 dm minus 6 to be the reciprocal form of the powers as shown in the indices law. So mole to the 2 becomes mole to the minus 2, and dm minus 6 becomes dm to the 6. And that means we brought these over the division line, and the s minus 1 is unchanged because it's above the division line when we move that bottom bit up, and that leaves us with the new unit of mole to the minus 2 dm6 s minus 1. So this table shows you some initial rate data. i.e. initial concentrations of reactants and the rates of reaction. I want to show you guys how to calculate orders of reaction from initial rate data information. So we look across the data for places where the concentration of one reactant has changed, but the concentration of the other reactants stay the same. So we can isolate the influence of that particular reactant on the rate of reaction. For example, let's look at reactant Z. When the concentration of Z was tripled, you will notice that the rate of reaction also tripled. This is a directly proportional relationship in terms of Z. We can therefore conclude that this is first order with respect to reactant Z. Next, we turn our attention to reactant X. Again, we have to look between two experiments where the concentration of X changes, but the concentration of Y and Z remain unchanged. This time we're going to look therefore between experiments 1 and 3. What we can see is the concentration of X has halved, and the concentration of Y and Z remain unchanged. We notice that the rate of reaction is unchanged and remains at 2.4 times 10 to the minus 3. Therefore, we conclude this is zero order with respect to reactant X. And finally, we look at reactant Y. Now, Y between experiments 1 and 4 has been multiplied by a factor of 4, whilst the others haven't changed concentration, and the rate of reaction is increased by a factor of 16. This is a squared relationship, and therefore we conclude this is second order with respect to reactant Y. So now we have all the information we need to calculate a value for the rate constant K. First, we write out the rate equation, rate equals K, Y squared times Z. We then rearrange the rate expression for K, K equals rate divided by Y squared times Z. Now we can calculate a value for the rate constant by taking some data from one of the experiments. I've taken my data from experiment 1. That gives me a value of 2.4 for the rate constant K. Next, we can calculate the units by replacing the symbols in the expression with the units themselves and cancel down moles per litre from top and bottom, leaving us with our new unit of S to the minus 1 over mole per dm minus 3 squared. In other words, mole minus 2 dm6 S minus 1. Right, so this is a slightly harder version of this sort of question. We have to use something called the interim rate to solve this problem. But actually, it starts off pretty similar to previous examples we've seen. We're going to look for an experiment where only one reactant changes in terms of concentration. So if we look between experiments 1 and 2, we can see the concentration of B has increased by a factor of 4, whilst the concentrations of A and C remain unchanged. And the rate has also increased by a factor of 4 as well, a directly proportional relationship, and therefore we can conclude this is first order with respect to reactant B. Now, between experiments 2 and 3, both B and A change their concentration. Luckily, we already know what B does because it's first order. What we do is work out an interim rate, the influence of B on the rate of reaction as if it was acting alone. So doubling B should also double the rate. The rate should increase from 3.2 times 10 to the minus 3 up to 6.4 times 10 to the minus 3 if only B was acting in isolation. But in reality, the rate has gone down to 1.6 times 10 to the minus 3. So what we do is we divide what the rate could have been if B acted alone, 6.4 times 10 to the minus 3, by what the rate actually is, and we find that it's 4 times slower than would have been expected if B had acted in isolation from our interim rate information. And we also know that during this time, A, the concentration of A, was halved. Therefore, when A was halved, the rate of reaction decreased by a factor of 4. This means we can conclude that this is second order with respect to the influence of reactant A. Finally, we need to look to experiments 1 and 4 to figure out the order with respect to reactant C. To experiments 1 and 4, we can see that A is divided by 2, B is increased by a factor of 3, and C is also halved as well. So we figure out the interim rate by taking 0.8 times 10 to the minus 3, dividing by 4 for the influence of halving A, which is second order, then multiply that rate of reaction by 3 to show the influence of B, which is first order, and that gives us an interim rate of 6 times 10 to the minus 4 if only A and B were acting in isolation from C. Now, if we look at the actual initial rate in the experiment shown, it's 0.6 times 10 to the minus 3. In standard form, that's 6 times 10 to the minus 4. That's exactly the same as the interim rate. That implies that C has had no influence on the rate of reaction, and therefore we can conclude that this is zero order with respect to reactant C because it didn't actually alter rate at all. And therefore we've calculated the orders for all 3 of the reactions in this rather tricky orders question. Thanks for listening. Take care. Bye for now.